I won't prolong the introduction, just a few words. This day of talks for some interested public audience is part of our Prague workshop in the Drake project. It's part of the 4E+ Drake project, where we focus on Drake equation as Nanna described. And this afternoon section of our talks will start with Nanna Bach-Møller from Denmark, from Copenhagen, and she is an astrophysicist and will talk about more astronomical terms in the equation, maybe those things we know more about than about the origin of life and such.
Yes. I will just switch here. Maybe. Yes, excellent. Yeah. So as you just heard, my name is Nanna. I'm from the University of Copenhagen, where I'm a part of the Center for Exolife Sciences, as you can see in a very small font down here. I work with exoplanets. So that is planets outside of the solar system, and more specifically I try to figure out how we can search for life on these exoplanets, because exoplanets are extremely far away, so this is a bit of a challenge. But today I will not just talk about the exoplanets, I will talk about everything from stars to these habitable worlds. And I will do so in the context of Drake's equation, as you have already heard before. But luckily, or I don't know if it's luckily, but you have very different levels about how much you know about astrobiology, it sounds like. Astrobiology, maybe I should say, is just the search for life in space or life in space. So astro, of course, is stars, like that includes all of space, and biology, of course, life. So that is what astrobiology is. It is just a search for life in space. And as I've written up here, there are three sides to this story, three different levels where we try to investigate life in space. The first one is the origin of life. So this is mainly based on life as we know it here on Earth. We're trying to figure out how the very first cells came to be. Also get an idea of what life even is. When do we go from just having chemistry to having life? Like, what is this transition? So that's very focused here on Earth. It has a lot of very heavy biology, of course. The next step is the solar system missions. As you probably already know, we are currently looking for life on other worlds in the solar system. What I have up here is a picture of Perseverance, one of the Mars missions that are ongoing right now, one of the rovers. And then we have two moons here, one of Jupiter's moons and one of Saturn's moons. These are very exciting because we believe they have liquid water, so that could also be a place to search for life. So all of this, of course, is very heavy in engineering, because of course you have to create the rovers. And that is, our immediate neighborhood, the solar system. But what I'm most interested in is a bit further away. That would be exoplanets. So those are planets outside of the solar system. So as you can hear, we have astrobiology on Earth, astrobiology in the solar system, astrobiology outside of the solar system. And each of these questions have very different challenges that we are tackling in very different ways. But for today, we will focus on the exoplanets. We will go outside of the solar system. Not for today, for right now. Later on, we will be looking more on Earth. Great. So what should we expect when we are looking for life? To be honest, we are not entirely sure what we should expect. We know that life exists in the universe because we have it right here. But we do not know how common it is, and we are not even entirely sure how to figure this out. But one way we discuss this is through, let's call it equations, or through expressions such as Drake's equation. So this is a way to try to figure out what we can actually expect. And the specific question we are asking here is, how many other civilizations should we be able to talk to? If we listen really well, how many should we be able to hear? And we don't know. But in order to figure it out, we try to break this question down in smaller sections. And I'll just walk you through those real quick. First, we're trying to go from, in order to have life, we believe that we need to have a system that life can live in. So we are moving all the way from stars and all the way down to smaller and smaller pieces. So first we'll just look at the formation of stars. How many stars are forming constantly? How many stars can we expect to have? Then we're moving on. Okay, so now we have our star. How many of these stars have planets? How many of these planets do we believe are habitable or Earth-like? Because Earth is the only environment that we know is habitable. How many of these habitable planets will actually form life? When we have life, how much of this life will become intelligent? how much of the intelligent life will start communicating in a way that we can hear, and for how long will this communication take place. So as you can hear, we're trying to divide it into smaller pieces that we can focus on individually. Right now, as you hear, I'm an astrophysicist. I will focus on these three first sections. So the stellar formation, how many of the stars will have planets, and how many planets will be suited for life. So, the formation of stars. And their planets, because spoiler alert, these two things happen together. I will try to guide you through it a bit here in the lower right corner, so if you at some point zone out and don't know what we are talking about, I will show you which of the factors we're going through down here. So, stars form constantly all the time in our galaxy. Happens all the time. The way stars form is that we will have a huge cloud of gas and dust, and this cloud can have existed for billions of years, for very, very long time. But at some point, a small current can start forming, clumps can form in these clouds, and when we have clumps forming, we will start seeing gravity act on the cloud. So the clumps will form, they will start collapsing, and when they collapse, they will also start rotating. So you can imagine they'll be coming from out here and very slowly move closer to each other, and when this happens, it will form a disk such as the one that we see here, a protoplanetary disk. In this disk, in the center of the disk, the gas and the dust will become so dense that it becomes a star. Nuclear fusion starts happening in the center of the star, and that is pretty much what defines a star in the first place. We have the star in here, we have still the disk of gas and dust around it, and in this disk we will see pretty much the same thing happening as with the star, so they will start clumping together and they will form planets. So all stars are born with planets, and all planets are born with the stars. So the solar system is all of the same age. The sun and all of the planets in the solar system were born together. So that pretty much answers our first two questions. So stellar formation, we can see this, we can observe it, we see it, as I said, all the time. We have plenty of observations of stars forming. So this is one of the factors in Drake's equations that we actually have a pretty good idea about. And we know that approximately 2.5, this means solar mass. So we have 2.5 times the mass of the sun that we can form into stars every year. So that is around 2 to 10 stars-ish, because most of the stars are actually smaller than the sun. So around 10 stars form each year. Great. So what about the planets? As we just heard, by now we think that pretty much every star will have its own planets. This is a pretty new knowledge. We had an idea that this would probably take place, but we haven't known of these planets, of these exoplanets, until 30 years ago. But for those 30 years, we have found more than 6,000 planets. So that's a lot, and we expect to find way more as time goes on. So we think exoplanets are extremely common, and we will have more planets than we will have stars in the galaxy, which is good if we are looking for a place where life can take place, right? Problem is, though, the exoplanets that we see are often very different from planets as we know them. Up here I'm showing you an illustration of the solar system on the bottom here. We have the sun, we have our 4 terrestrial planets. This is Earth, as you can see. We have our 4 smaller terrestrial planets, and we have 4 gas giant planets. So these are significantly larger and made mainly just of gas. And we thought, okay, this is probably a pretty common system. This is what the solar system looked like, this is probably what we will find. But this is not what we find. Most of the systems that we find have significantly fewer planets. Oh, by the way, these two are examples of very common exoplanet systems. So this is what we see when we look up on exoplanets. We see a lot of lone planets. We see a lot of gas giants, so like Jupiter, for example, that are very close to the host star. This is what we call a hot Jupiter, because we're not super creative, and this is a hot planet that looks like Jupiter. But it's alone. So what we think happened is that the gas giant from out here moved in through the system, created complete chaos as it moved, and then ended up very close to the host star. We also see a lot of very compact systems over here, where all of the planets are more or less of the same size. As you can see down here, these are very different sizes. But these are pretty much all of the same size. And this seems to be the norm. We call it piece and apart systems. And to make it even weirder, most of these planets that we find, or a lot of them, are of a type that we do not have in the solar system at all. It is what we call a super-Earth or a sub-Neptune, as I write up here. So it's a few times the size of the Earth. And these are what we usually see, which is weird, because this is not what we expected, and we're not entirely sure what this means for us if we want to look at planets or systems that are very similar to the solar system. But nevertheless, the question was just how many stars do we think have planets? And we can say pretty much all of them, almost 100%. Okay, great. So now we are already 2 terms down in our Drake's equation, which I can see is very difficult to see up here, probably because of the light. We're already 2 terms down. Easy, we could just continue doing this all the way through, and we will have answered one of the biggest questions we have in, human history. But sadly, it's not as easy as that. Because already when we move on to the next question, namely, what does a planet need to have life on it, it becomes significantly more tricky. So what does life need? Do anyone have any suggestions of what life needs to exist?
Water.
Water? Someone said water. Excellent. Anything else? If you figured it out, could you let us know? Because we have, I won't say no clue, but a limited number of clues. So if you figure it out, please let me know. It would be very, very important for the field in general. We're not entirely sure what life needs. We only know one type of life, and that is the life here on Earth. And we are trying to predict how similar life outside of the Earth will be to the life that we know here on Earth. Someone said liquid water. That is the only thing we are relatively sure of. Because life, as we try to define it, to be honest, we are not even really sure of what it is. But as we define life right now, it is a self-sustaining chemical system capable of Darwinian evolution. So maybe just based on this definition, we can start getting some clues. Okay, so it's a chemical system. This means that we need chemistry to be able to take place. Chemistry takes place everywhere. Chemistry takes place in the atmosphere, it takes place on this table, it takes place everywhere. But the best place for chemistry to take place is in a liquid. And particularly water is very, very good for chemistry to take place because it creates a medium where all of the molecules can meet each other and react without interfering with the chemistry. So other liquids could be possible, but we think water is the best one. So that's the reason we think all life needs water. Also because we can see, no matter what kind of life you look at, we are pretty much just a collection of water balloons. All of our cells are filled with water. We have so much water. So we think water is important. Then we need for it to be self-sustaining. This means it needs to be able to pull energy from its surroundings to maintain itself. In order to do that, you need to know what is you and what is your surroundings, because otherwise you can't pull energy to maintain yourself. So we think we need some kind of boundary. Up here I'm showing you a very simple cell. This could be what the first cells here on Earth looked like. It could be a different kind of boundary, but we think we need some kind of boundary. And then it needs to be capable of Darwinian evolution. This means you need some kind of genetic material. So we need liquid water, we need molecules for the chemistry to take place, and we need energy. And this is the only thing that we're sure of. But that doesn't put a lot of constraints on our planet, sadly, and on the environment that we're looking on. Or maybe it puts a lot of constraints. We're not entirely sure about this. But first, let's look for our liquid water, because we was pretty sure about that one. Water, or H2O, is extremely common in the universe. We see it everywhere. But we mainly see it as an ice. Because when water goes below 0 degrees, you already know that, we are getting closer to winter. I don't know how much snow you're getting here. But as soon as we go below 0 degrees, our water will start to freeze. So we need to be able to, we need to have a temperature. Also if it becomes too hot, if it's above 100 degrees, it will evaporate and become a gas. And none of that is very good for chemistry. We need it to be liquid. So we need just the right temperature for water to remain liquid. And this is what we call the habitable zone. So the habitable zone is the distance a planet needs to have from its host star to have the right temperature for water to be liquid. As you can see, this is the inner parts of the solar system, so these are our terrestrial planets. And as you can see, the Earth is very nicely within the habitable zone. This is great. We can have liquid water. Everything is beautiful. Mars is just on the outskirts of the habitable zone, so maybe, in theory, that could also be interesting. And Venus is just on the inner side of the habitable zone, so that could also be interesting. If the solar system was an exoplanet system, all of these planets would be very, very interesting for us because they could support liquid water. If we compare, down here we have the solar system, and we compare to one of the most famous exoplanet systems. I don't know if you've heard about TRAPPIST-1 before. So TRAPPIST-1 is a system with a lot of more or less Earth-sized planets, as you can see. And maybe you remember I showed you before that in a lot of exoplanet systems, all of the planets will have more or less the same size. TRAPPIST-1 is a perfect example of this. TRAPPIST-1, this star in here, is a different type of star than our star. Our star is what we call a G-type. It's a medium-sized star. Not super big, not super small, and relatively bright and hot. TRAPPIST-1 is a tiny star. It's what we call an M-dwarf, also the most common star that we have in the galaxy. But it's also significantly colder. So in order to be in the habitable zone, you can see that all of the orbits that we have here, they are all within this region in the solar system. So it's very, very dense. It's a very small system compared to what we have. But you can also see all of these planets up here are in the habitable zone. So if we just go by temperature and potentially liquid water, these could all be planets that are very interesting when you search for life, because they could, again, have liquid water. Okay, so now we found our liquid water. Oh, well, we didn't find it. We think we might have found a place where there could be liquid water. But how do we find out if it actually has liquid water? Because these planets are so far away, it's very difficult to see them. Our observations of them are not super good. This is an illustration, by the way. This is not a real picture, just to be extremely clear. If anyone shows you a pretty picture of an exoplanet, it's a lie, okay? It's just someone who got creative, because sadly our telescopes are not that good yet. So we cannot see the surface of the planet. We cannot see the liquid water. What we can see, though, in many cases, is the atmosphere, so the layer of air around the planet. And if you have liquid water on the surface, you will also have water vapor in the atmosphere. So we can try to look for that. So what we do is that we wait for the planet to pass in front of the star. Then we look at the light from the star passing through the atmosphere of the planet, and that will leave a fingerprint depending on the molecules that are in the atmosphere. The atmosphere will absorb some of the light coming from the star, and from whatever passes through and reaches us, we can tell what the composition of the atmosphere is, so which molecules we have there. So this could look something like this. This is what is called a spectrum. Here you see how much light we have at different wavelengths, so that is different colors. And this is the fingerprint that I talked about before. So this is for the exoplanet WASP-18b. Here they have marked some interesting zones, because all of these are the fingerprint for water. So by looking at this, we can tell, okay, this planet has water vapor in the atmosphere. We don't know if it necessarily has liquid water on the surface, but if it's in the habitable zone and it has this feature, that is a very promising sign. So this is more or less what we are doing when we are talking about looking for water on planets. But what else do we need? We are not entirely sure. We are not entirely sure, sadly. Again, we only have one type of life. We only know of life here on Earth, and we don't know why we are here and not on any other globe. Maybe the surface is important. Maybe it's important that we both have an ocean and a surface. Some people think that a surface is necessary in order for life to form in the first place. At least we know it's necessary for us to, walk around and do things. If we were in the oceans, we wouldn't be able to do nearly as much as we're doing here on the surface. So maybe that's important. Maybe we need a specific type of star. As I told you before, some of the stars that we are looking at, some of the small red stars, are very different from the sun. They are way dimmer, but they also have higher activities. They have more solar flares or stellar flares and stellar storms, as you can see up here. And we are not entirely sure how that will affect life. Maybe we need the moon. Our moon is very, very special. We don't see any other moons of our kinds. It's extremely big compared to our planet, which is unusual when we look around. We don't know if that is necessary. Or we don't know if we need a certain type of system. Down here again, I'm illustrating the solar system, and as you saw before, exoplanet systems don't look like us. We don't have as many planets. The systems might not be as stable as ours. And we don't know if it's important to have these giant planets out here in order to protect the inner systems from asteroids and comets and stuff like that. All of this might be extremely important or not important at all. We don't know. So when we ask, okay, how many planets are suited for life? We don't know. If we say, okay, so how many planets, we don't know. If we say, okay, so how many planets are in the habitable zone? That would be 0.2 planets per system. So this is pretty good. But if we also need all of the other things, maybe we have none, or very close to zero. We don't know. And these were just the 3 first terms of the Drake's equation. These are supposed to be the easy ones. So I think you should be very excited when we're moving on to some of the later talks today, because they will dive into the origin of life in the first place and what we need in order to form intelligence. It's tricky. Okay, so then you might ask, Nanna, you're an astrophysicist working with exoplanets. You just told me that we don't know shit about all of this. So what are you even doing? I'm so glad that you asked. So, yeah, Drake's equation again. What are we trying to do? So what we're trying to do is, instead of knowing exactly what we need in order to have life, we will try to just search for it in general. We look wide, and we're trying to look for life as we don't know it. So, of course, we have life here on Earth. We understand this. But we don't know what all of the life forms outside of Earth would look like. But if we return to the definition that we have before, a self-sustaining chemical system capable of Darwinian evolution, again, this might give us an idea of what we can look for. Because, as I told you before, in order to sustain itself, life will draw energy from its surroundings, and in doing so, it will also change its surroundings. We do that here on Earth all the time through breathing, through what we call metabolism. So constantly, all the time, while I've been talking, while you're sitting there, we're breathing in one type of air, we're breathing in oxygen, we're breathing out CO2. So we are increasing the amount of CO2 in this room constantly. At the same time, all of the plants, a lot of the bacteria outside is breathing in CO2 and breathing out oxygen. So we are constantly changing our atmosphere. And this is something we can look for. If we look at Earth's atmosphere today, we will see a lot of nitrogen. This is life, clearly, you can all see that. We have a lot of nitrogen in the atmosphere, but the second most abundant molecule in the atmosphere is oxygen. And we should not have oxygen. It's super weird that we have oxygen here on Earth. The only reason we have that is because of all of the plants and all of the bacteria that we have, especially cyanobacteria are doing quite a lot of the work. This is what the atmosphere of Earth would look like without life. We would not have any oxygen, as you can see. We would have significantly more CO2. We would also have some ammonia, CO, and hydrogen. So if another alien species around an exoplanet somewhere was looking at Earth, even without knowing what Earth life needs, it would know that something is very, very wrong. And this is what we are trying to do when we look for life as we do not know it. We are trying to look at this effect we have on the surroundings. This is called the disequilibrium. You don't need to remember that word. But this is what an equilibrium atmosphere would be. This would be an atmosphere out of balance. So we're looking for atmospheres out of balance. And the way we do that is similar to what I showed you before. We're looking at the light passes from a star through the atmosphere of a planet, and then we're looking for the fingerprints. I don't know, how many of you heard about K2-18b in the spring? Some. K2-18b is an exoplanet, and it was very exciting in the spring because someone had been observing this exoplanet, and they said, hey, we have been looking at the exoplanets. We can see signs of the molecules dimethyl sulfide. Is that, now I'm looking around, is that how you pronounce it in English? I think maybe. DMS and DMDS. These are both molecules that, according to them, should not be there. If the atmosphere is in balance, if there is no life affecting the atmosphere, they should not be there. But they are there. And here on Earth, we know that they are formed by microorganisms. So here on Earth, we know that these molecules are formed by life. This study is very uncertain. There are a lot of things going into it that we are not entirely sure of yet. So please don't take this as me saying, hey, we already found life, job's done. Because we still need a lot of things to happen before we can conclude that. But it was just to show you this is how we do it in general. So yeah, I don't know how much time I have left. Would you like a summary, or are we nearing the end, Jan?
I think you have like 10 minutes.
Excellent. Okay, perfect.
We have some time for discussion, 10 to 15 minutes, right?
Perfect. I will do this very short. It is also short. So, stars form with their planets. We understand this. Good job, us. Exoplanets can be very different from solar system planets. We are starting to understand this within the last 30 years, and more will happen in the next years. And we are pretty sure life needs liquid water, but what else? We do not understand this yet, but we are working on it. So this is the state of these three factors at the moment. That was all from me. Thank you.
Amazing. Thank you very much for your talk.
You're welcome.
Now we have some time for discussion. So do you have any questions? Okay.
So thank you for your talk. I would like to know, because it was also mentioned that we have also binary star systems. So how is this included in the Drake equation? That's it.
This is a very good question. It's one of the things that will be discussed later, that right now the Drake's equation, the way it's written, you can take all of these factors and ask questions about them, like try to figure out what exactly is the right factors to use. I would place binary stars in here and say, okay, so how many stars are forming that are relevant for the search for life, if that makes sense. Because of course there can be so many different types. So it's a bit difficult to make a direct translation from all of the very specific cases and then place them in the Drake's equation. I would place them in here, but it would depend on what question you are asking, if that makes sense. We're not entirely sure how binary stars affect the habitability of a planet. My guess would be it's not helping. Because again, we might need a very stable system, and binary stars, suddenly you have two very huge stars that are affecting all of it. So they might not be the best place to look. Sadly, we had a lot of them, so yeah. Did that more or less answer your question a bit?
Okay.
Okay,
yeah, thank you.
Yeah, hi. I would like if you could more comment on this approach on having liquid water as a condition, because I can understand that there are quite a few reasons, for example, to stay maybe with carbon-based chemistry, because there is very big difference between the reactions of carbon and other elements, at least in some more or less explored range of conditions. But I'm not sure why water should be that much exceptional, and especially the liquid water on the surface. Even with water, there are quite a few ways how to get to it, even in, for example, in form of aerosol or vapor. So why this is, in current state of knowledge, considered a condition?
This is a good question. Yes, so why would liquid water be a condition? Again, as you were saying, like the chemistry is very, very important, both for life when it's already there. Like we are just a bunch of chemical reactions all the time, right? So for us to maintain our chemistry, we would need some kind of medium for that chemistry to take place in. So in us right now, we need a liquid medium, which, as I said, the best one is water. You could have other ones. I know that methane is being discussed, for example. We have a moon called Titan. That was one of the pictures I showed you earlier, where there are methane oceans. That could also be a suggestion, but methane meddles way more with the chemistry than H2O, than water does. Water is very neutral. So it doesn't affect the chemistry, it doesn't affect the molecules as much. So it allows for more flexibility. So it's not the only option. It, as far as I am informed, most likely the best option. It's the most versatile option. In the same way that you could say, you mentioned carbon chemistry, we are mainly based on carbon. You could also imagine other molecules that could be in place of carbon. None of them are as versatile and as good as carbon are. So we do think it might be some of the best options for this chemistry to take place. You look very puzzled. Do you have a comment?
Yeah, because I understand that this is kind of, let's say, safe way of thinking, because we obviously have a well-developed example of water-based life, but I have a feeling that it is kind of unnecessary self-imposing condition, because it's like, for example, oxygen metabolism was actually at the first point was kind of poisonous, yeah. And actually water water must be actually well contained in Earth's organisms to actually withstand the water. So the feeling that the water is somehow more friendly to our chemistry is maybe just our ex post feeling that from the life that already handled the living in water. So
I completely get your point. I thought the same thing in the beginning. I thought people were just being, setting limits to our search just because we're looking for ourselves. We always have a tendency to look for ourselves, right? Because we think we are oh so special and everyone else have to be like us, especially in order to be intelligent, but that is a different discussion. So I very much get where you're coming from. I was coming from the same place. Oxygen, as you're saying, is extremely toxic to a lot of life forms. Oxygen is not very good for chemistry because it's extremely reactive. So oxygen is actually the opposite of water in that case. Water is conducing to chemistry. Water does not break things down. It does to some extent, but not nearly as much as many other liquids. So water is actually the opposite of that. On top of that, we have crazy amounts of water. Like water is built from hydrogen, which is the most common atom in the entire universe, and oxygen, which is also extremely common. So there is a lot of it. It has a very wide range of temperatures where it remains liquid. Most other liquids have a narrower temperature range where they can be liquid, otherwise they are solid or in gas form. But water can have a very wide range, and you can actually have all three phases of water in more or less the same environment, which is also extremely good. So water is just the best suggestion we have. Others might very well be possible, but they are, as far as I'm aware, I'm not a chemist, but as far as I'm aware, not as good. So, but carbon could in theory be something else. Oxygen we're not looking for, well, we sometimes looking for oxygen, but oxygen we do not think oxygen is necessary or necessarily a very good sign for life because it's so reactive. Even many of our cells or many of the processes in our body cannot handle oxygen. So it's a bit of an explosive one, that one. So did that answer your question?
More or less.
More or less, okay, yeah.
Thank you.
Okay, anyone else?
Just one remark as concerned the surface, if it is needed or not. I think that maybe for life as a whole, it is not needed. But in my opinion, it is extremely needed for technological civilization. I think that without a surface, there is no possibility of have a technological civilization.
Yes, this is a very widely acknowledged opinion. So I completely, yeah. So the thing that was said was that a surface could be very important for technology and maybe even civilization and intelligence to develop. And I completely are with you on that one. It might even be necessary to have a surface for the initial formation of life in the first place. A lot of people believe that the switching back and forth between being liquid and drying out could be important for building up the chemistry needed for life to form. So wet-dry cycles is what they call. A lot of people think that life formed in tidal pools, so small pools that would sometimes have a lot of water, sometimes have less. And in order to have that, you cannot have that in an ocean, right? Because you would have a lot of water all the time, or another liquid. So it might even be important for the formation of life in the first place, but it's definitely important if we're looking for civilizations. Or not definitely, I don't know what life could do, but probably important for looking for civilization. So that's a very good point, yeah.
Julian?
Thank you. So there are many large rocky planets, some of them due to their density likely with a large fraction of water or other volatiles. But there is an ongoing debate whether having a high-pressure ice layer at the bottom of an ocean is prohibitive for the origin of life or not. So given our ability to study exoplanet atmospheres, are there any markers that we could use to distinguish whether the ocean and the atmosphere are in contact, or reaction speaking, with the bottom? Basically, can we tell with some reasonable level of certainty whether the high pressure ice is convecting or whether there are any eruptions?
I will have to say no, but this is important. Sadly, the only thing, as I showed you on the photo before, the only thing we can pretty much see of the planets, in some cases you might be able to see variations in the reflectance on the surface, so that could give you an idea of what's going on the surface, but in the vast majority of cases, this will be the only thing we can see. So we can see the atmosphere. There will be interactions between the atmosphere and the lower layers. That will always happen to some extent, but often it can be very limited. If you look at the atmosphere of Earth, I'm not even sure that you would be able to say that we have soil. I don't think you could necessarily tell exactly what our surface is composed of. And you would definitely not be able to talk about, what the mantle and all of that, as far as I'm aware. So it's very tricky. You can see some molecules. I can imagine maybe you could see some of the remnants of volcanism or something like that, and in that way you would know that there is some kind of transport from the inner parts of the planet to the atmosphere. But it is tricky. Sadly. So might be very important, might be impossible to see, at least as we are right now. But people are working on it. I know that there are a lot of surface atmosphere research going on that is hoping to find some telltales that can put us in one category or the other. Yeah.
Okay, thank you. And I think we have time for one more question. Does anyone have a question? I have a question. Okay. My question is, there has been a talk of not only the classical habitable zone, but also so-called galactic habitable zone, maybe depending on the density of stars and star rate formation and such. What's your opinion about this?
Yes, so the galactic habitable zone. So as we talked about before, there is the habitable zone around the planet. That would be the right distance from the planet where a planet could be habitable. And some people are talking about the same things about galactic habitable zones. So do you need a certain distance from very high energy situations? That could be the center of the galaxy. It could also be regions with high stellar formation. Do you need to be in a certain part of the atmosphere in order for your planet to be habitable? I would say I wouldn't place the planet at the center of the galaxy. Of course, there are some limits with very high dense environments that are not most likely very conducive for life, simply just because the planets are pulling at each other, no, not planets, sorry, the stars are pulling at each other so they can disturb the systems. And again, maybe stability is important, so that would not be the best part. I think I would go for like no-go zones. I don't think, well, not no-go zones, but you know, less promising zone. I don't think I would talk about necessarily a habitable zone in the galaxy. Also because we're not entirely sure how much the galactic environment even has to affect the planet as a whole. So, but it is being discussed because that could also be important. Yeah. Right now, pretty much the only zone we can explore for exoplanets is right around the sun. So we are not going very far into the galaxy, like we're not seeing planets very far away. It's just in the solar system neighborhood because we cannot see that far. And so that is also, it's not super necessary to understand with the exoplanets we are looking at right now, but it could be important when we are talking about like the wider scale.
Okay, thank you very much. And thank you again for your talk and for the discussion. And now we have 5 minutes, so a short break, and then Nicolas Francis will start with his talk.